We're going to continue to introduce binary search trees in chapter 25. All right, here's a quick review what we have done last time. We introduced the data structure of binary search tree and the definition of a binary search tree. And we look at the search algorithm. So how do you perform a search in the binary search tree using the search property? So let's quickly look at it. It's the search an element in a binary search tree. So here, this is what we. Okay, I'm going to mute everyone. Okay. All right, so when you do a search, perform a search, you're going to start from the root. And if the root is not null, so you're going to compare the element that you're going to search with the current one. So the current one starts from the root. So if it's less, you go to the left. If the right, goes to right. And otherwise, that is going to be true. All right, if you go through the search, you don't find anything. So your current is going to be null. See, every time you have, if it's less, you go, your current go to the left. It's the current dot left is assigned to the current. And goes to the right, its current dot right is assigned to right, to current. All right, so now let's look at the algorithm and for this insertion. So how are you going to insert it? So this is what we're going to insert it. It's we're going to look at this. If the tree is empty, so you're going to create a new node. That new node becomes the root. So otherwise, we're going to search to locate a position for the new element. So when you do this, and you're going to have this two references values, current and parent. So the current is where you're going to start the search, and the parent is the parent of the current. So initially, so we're going to have this, and current and root are the same. So this is the root is assigned to current, and the parent is also the current now. So now look, if this, we're going to through this while loop. If current is not null, we're going to compare this, the value you're going to search. If this is E, if it's less than current dot element, so we're going to have this as part assign current to parent, and now the new current is current dot left. So now you see that current and parent, so they're all together. So if it's greater, we go to the right. And if it is equal, so that means, and it's already in the tree, we're not going to insert it. We assume that it's a unique, the situation is all the elements here in the tree are unique. Return false. All right, so if you do all this, and when this while loop ends, so here, if this is the current is null, so that means the element is not in the tree, we're going to insert it. So now we're going to insert it right here. We're going to create a new node and then attach it to the parent. So here is the illustration here. So let's see, we have this tree. We're going to insert this as the 101. So 101 is greater than 60 and greater than 100 and less than 107. So 101 is going to be inserted right here. So this is going to be, so here is going to be the parent is. So now you're going to see this is the parent. So this will be the current now. Next, we're going to insert 59. So 59 is less than 60, greater than 55, greater than 57. So it's going to be inserted as the right child of 57. So it is going to be like this. So that's how you're going to search it, insert it. So this is the algorithm for insertion. So this is insertion algorithm. And now let's go down to the quickly look at the traverse. You have all the elements in the binary search tree. So there are a couple of ways we're going to traverse it. So we can look at in order, pre-order, post-order, depth first, and breadth first. All right, so now what is in order? All right, so you click on in order. So this is the in order, you traverse everything. And in order is this. This is how we traverse in order. Is we're gonna start from root, but we don't traverse the root yet. We're gonna do it recursively on the left subtree, recursively performing this in order. And then we visit this 60. And then finally recursively on the right subtree, performing in order. So what you're going to see, this is the order of the visiting. It's a natural order. It's so 55, 45, 55, 57, 59. You can see this is in order. So the name of this order is called in order. So that is everything in order. So this is the in order traversal. It gives you the sorted sequence. All right. So this is the recursive definition for this in order. And also now let's look at the post order. It's recursive definition for post order. So post order is this. We're going to start from this root, but so here we're not going to visit it, and we do it recursively on the right subtree, and then recursively on left subtree, and then we do the recursively on the right subtree, and finally and the root. See, now this is the post order. It's the post order right here, post order. As you see here, and 60, the root is going to be the last one to be visited. So what you do is left, right, and the middle. So recursively, the key word is recursively. So when you do this left subtree, again, it's recursively, and you do the left subtree here for this 45, and then you do this one right here. It's the right subtree, and then you do it recursively. So this is going to be 59, 57, then 55. So this is the post order traversal. Now this order traversal has applications in the future. You're going to see it with different ways, and we're going to have different applications. So now the pre-order. So let's look at a pre-order. Pre-order is this. You're going to start from root, and yes, you first visit the root and then go recursively left and then recursively right. So first is 60, and then this is 55, and then 45, 57, and 59. So this is here. And then do it on the right, recursive. All right, so what is depth first? Depth first is you go all the way as deep as you can. Go and then backtrack. So it is depth first. And so it go down like this. It's this. It's called depth first. And breadth first is level by level. So you go first is 60, and then 55, 100, and then this 45, 57, 67, 107, and 59, 101. So level by level. This is called a breadth first. All right. So let's look at this. You can play with this, and so let me open another tab. another tab, and look at the at this animation. So here is this is the animations here. So you can look at the animation right here. And so here, let's see, what is in order? So you click on this in order, you can see that it's going to be this 25, 35, 50, 80. So that's the in order. That's the in order. So what will be the pre-order? Pre-order is going to be 50, starting from 50 and 25, 35, then 80. So that's the pre-order. And so what is the post-order? Post-order, you are going to go this recursively on the left, and then on the right, and finally, this last one is 50. So this is going to be 50 is the last one you see. This is here. All right, so this is the tree traversal. And next, so we're going to look at the design of this data structure. So this is not in the Java API. It is useful data structure. So we're going to design it ourselves, and then we're going to implement it. So we design it. So this is UML diagram for this our design. So here is this is binary search tree. So we're going to make this binary search tree as this interface of the tree. We're going to have this interface of the tree, and have this common operations defined in the interface. So we're going to have to implement this tree here. And then we're going to make this as a subtype of Java API collection. It's in the Java API collection. So that's the collection we are familiar with a lot of common operations for the collections. All right, so this is the method search, insert, delete, and get size, in order, pre-order, post order. So this is we're going to design all this, okay? And so this is the interface, and here is we're going to design this is BST. So internally we're going to have the root size, and this is the comparator to compare the elements. Now, please note that this is the pound sign means it is the protective visibility. So the protective visibility, it is very good. And what we need to do is when we going to use this next chapter, we're going to have another tree. It's called AVL tree. AVL tree is going to be a subtype of the BST. So the AVL tree can access this or this root size and this comparator. So if you make it a private, and then we'll not be able to access it from the subclass. So we make it a protected. So this is a good visibility here. All right, so here, the constructor, NOA constructor, the constructor with a specified comparator, the constructor with, if you have array of elements, you can put it in. And there's another useful method. We're going to do a path. We're going to find a path, something it's useful here. It's from the root to any node in the tree. So that is the path. So here's this notation. It's the solid diamond. And so this is the this is containment. So this BST contains all the tree nodes, and the tree nodes are linked together. And so here's each tree node has this element, and left to right points to next tree node. So we're going to write the code for this tree. So here, so please note that this is the interface extends java.util.collection. Okay, so this is the one. So we already have this imported java.util, so that we don't have to do anything here. And we have this search, insert, delete. So this is get size, in order, post order, pre-order. And now we're going to implement some of the methods in the collection interface. So these are the override. So is empty, contains, and you can write all this implementation. So you can implement this and see how you write this all this code here. Okay, how to do all this code. So I'm going to leave it for you to write all this code here. Now let's look at BST. So BST is going to implement tree. That's the one we defined, right? And with this, protected the root. A root is tree node, and the size now is by default is 0, and the comparator is C. So here, this BST is, and this one here is using natural order. So the natural order, so how you do this natural order, and so it's the comparator. You have to have a comparator here. So this one, this constructor, you have a default comparator. So you can have this C dot is assigned the C here, and this one, and you have to do this sum, write as sum of the lambda expression here. You can continue to write the lambda expression for this. Okay. All right. So this is the search, and this is insert. We already had the algorithm, and we just fill in the code. So how you write this code. So look, please, and practice this, and after the class, and see how you do this. All right, so now there is interesting thing is about this protected create a new node. So creating new node, we know it's really simple, just new, and with tree node you create it. So the reason I'm going to put this is for the subclass to use it. So this because subclass were creating different kind of tree node, so we just put it. So this for now. So when you have this is now you just return new and tree node and E. So here is the element for this. Just return this. But this is protected. It's very useful. We're going to override it when we have the new subclass, the aviary tree. So that's the design. It's a very good approach for this. All right, so everything here, and so please read this and see how you're going to do the in order and do the post order and do all this. All right, so this is the how you do all this things here. All right, so next, I'm going to keep this. I'm going to start a new tab here. Let's have a new tab. So we're going to have this new tab and look at this. This thing here is the how are you going to delete elements from a BST? Okay, so this is, we don't do it arbitrarily. So we have to have an algorithm, a systematic way to delete an element from a binary search tree. All right, so we're going to consider this actually two cases. So first thing is we need to do a search to identify the element. If you don't find it, and then you cannot delete it. So that's going to return false, that the element is not in the tree, right? So like this, if you go here, if you say, I'm going to delete 55. So if there's a remove 55, 55 is not in the tree. So 55, the key here, key 55 is not in the tree. So it's not in the tree. You cannot delete it, okay? All right, so if it is in the tree, so like this is 25. So if you remove 25, you can delete it. So we're going to consider this two cases. This is the current one. It's the one you're going to delete. So here is the current one, and you are going to delete this one, current one. So the first case is this. the current node does not have any left child, no left child. That's the case. All right, that's the case. And the one case. And the second case is the current node you are going to delete has a left child. Okay, so the case one, you cover all the cases, has no left child and has a left child. All right, so that's case two. Case two is this one has a left child. That's case two. So for case one, and really simple is what you're going to do is, hey, because it's does not have left child, you're going to connect this subtree, the right subtree of the current to the parent of current. So like this. So here's the example. You have this, if you're going to delete 10, so what you're going to do is 10 does not have a left child. So you're going to connect 16 with 20. So this like this. All right, so that's the case. And you can go here. I'm going to show you here. I'm going to run this. It's this 25. I'm going to delete 25. See what happens. 25. You're going to connect 35 with 50. Just delete this. All right, remove. Set 25. So we're going to find 25. 25 is less than 50. 25 is here. All right, so now look at this. We're going to delete 25. 25's left is null. It does not have a left child. So we're going to remove 25 by connecting 25's right child. All right. In this case, it's 35 with 50. With 25's parent. 25's parents is 50. Okay, so that's it. All right. Okay, so let me add another one here. Is I'm going to put something back here. Is this? So let's add this 25 back. Insert. So where 25 is going to be, you add 25 back. Can you tell me where 25 will be after insert? 25. Hello? Are you with me?
Yes.
Okay, so where 25 will be? When you insert 25 to this tree?
It wouldn't still be on the left?
Yes.
Left
So,
child of,
yeah, left child of 35. So this is where you go. So here. All right, so like this. Okay, let's go back here now. The second case we delete is this. We're going to delete this. So here is the current one, we find it, but the current one, this case has a left child. So what we're going to do is, this means it has a left subtree here. We're going to find the rightmost. So find the rightmost one here, somewhere here, and then this is the rightmost, and replace this current with the rightmost one, and then connect this, the left child of the rightmost with the parent of the rightmost, like this here. See this one here. This one is now, the value is here, copied into this. This is going to be deleted. So here's the example. So now we're going to delete 20. So which one is the rightmost? Is 16. So now 16 is copied here, and 14 is connected with 10. So that's it. All right, here is the algorithm, how we do this in these two cases. Okay, so we're going to do this. Writing this code here is delete. We're going to first locate the element in the tree. If this element is not found, we're going to return false. And so now let's have this current be the node that contains E, and the parent be the parent of the current. So we can consider these two cases. So this is case 1 and case 2. And so finally going to return true. So this is deleted. All right, so let's look at this example here. Okay, now we're going to delete this 50. So let me add a more node. So let's make it more interesting here. So here I'm going to have this is 45. So where 45 is going to be inserted, it's going to be inserted as right child of 35. So this is 45. Okay, so let's add another one. It's 42. So here is 42. All right, so now I'm going to remove 50, 50. So this is 50. We're going to remove it. See what happens? This is the case 2. And which one is the rightmost child in this left subtree of 50? It's 45. So you're going to see 45 is going to be used to replace this value 50, and then connecting this 42 with 35. So that's how it's going to work. So here is this. And this is case 2. 50's left is not null, and remove 50 by replacing 50 with the largest value in the left subtree. So that is this here, 45. And connect 45's left child, if any, with 45's parent. So this is the one here. 42 left child with 45's parent is 35. That's it. All right, so now let's delete 35. So if you delete 35, and this is the case, is 35 has a left child, 25. So here in this left subtree, and 25 is the largest value, it's the most right value. So that's the here. And 25 is going to replace here, and there's no here, nothing here, just assign this no value into the left child of 35. You can see this is how it works here. 35, we're going to remove 35. And this is the case 2. So now you see this is the case 2. All right, so please study this and see how this works and with all this algorithm. And now I'm going to go back to this algorithm again, and you can see here how this is implemented in this source code. So here, how we implement writing code for this. Okay. All right. So let's look at this here, everything here. Let's open another tab here. All right. Next, so please look at this very interesting way to visualize the tree. Okay. So we're going to look at this is the writing this JavaFX program to visualize the tree. So we have the tree, and you can see this here. We have this is the animation. So this animation here is developed using JavaScript. And so behind this JavaScript here is data structure, the tree there. And what you see here is visually, this is all this visual representation of this binary tree. So I want you to see if you can write your code for this visualization and using a Java code. And using Java code, we use the Java FX. So writing this in Java FX is this. So you have insert and delete. So let's do a simple thing here. You can add on more buttons. And like do a traverse or in order, post order and pre-order, all this. So this is the things I want you to see if you go back to read it and how this is done. So this is typically it is the model view control architecture. So it is this. So we have the model. It's a data structure here. The model you store data in the data structure, and you have a view and to display it, and you have this in the middle to control all this. And so you have visual presentation, and you can interact with data and all through this view and the controller, and works to control the data access. And so this is very typical and design. It's a pattern, and when you do all this visualization with data, so this is how you hide the data behind the scene, and so you control the data and display it. All right, so please study this. Okay, I guess I'm going to do the next thing is implementing the iterator. So I want to traverse all this. There's iterator here. So if you look at this, here we have the iterator interface in the Java API. You create iterator, you're going to have has next, has next, has next, has next. This is next, 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 all those things. And so you're going to do a traverse here. So we actually, I wanted first to show you the test code. If I have, this is my binary search tree. Look, this is my binary search tree. So I'm going to insert. So this is using natural order. So this is the order here I'm using. It's a natural order. Okay. Alphabetically and for the string. So this is the all this numbers here. Green, okay, maple, teal, and blue, jet, purple, Danube. So this are the color names here. All right, we're going to traverse everything. Is going to write this. So I'm going to be able to use using iterator. You can use the iterator. So because this BST is a subtype of the collection interface. Collection interface is a subtype of iterable. And from iterable, and you have the method, you can get iterator. So if you don't write this for each loop, so you can rewrite the code and using explicit iterator. You can write this code like this here. So you can write here is getting this iterator, is this is iterator, is a string. So here is iterator, is object here, How do you get it? This is BST. This is tree. Here, tree dot iterator. All right, so you're getting this iterator. And then you write this while loop, why this iterator dot has next. All right, so then you're going to get the next. So you can write the code is like this. It's writing this code here, system dot out dot print. So I'm going to print this. So here is going to be iterator dot next. All right, and then this is a string. Convert the string into all uppercase. So you can write this code. All right. All right, but we know if you have iterator, you can always use in for each loop or for each method. So we're gonna rewrite this code and using for each. So instead of this, I'm gonna rewrite this and using this for each method. So here is for each string s in this tree. So we're gonna do this. So this is the code. All right, so if you can run the code and just see how it works, you do it twice. All right, there's a problem with iterator here because I don't have this java.util. I have to put this util.iterator there. All right, so this is everything works, and you see this, it's everything here twice. All right. Okay, you can comment this now. Comment this, and so you're gonna do it only one time. So you're gonna run one time. Okay. All right, so you can also change this comparator. Instead of doing this with this order here, it's the alphabetic order, increasing order. If you want to do a reverse order, so you can write in many different ways. You can simply, and using this java.util.collections. Remember, there's a reverse method. It will reverse the natural order. So I think this is reversed. Let's try this. Maybe I remember it. Let's see if it's reverse. I think it's reversed. Maybe just reversed, not reversed. Okay. Reverse. Don't remember exactly. Maybe I'm going to check on that method. But anyway, you can do it different. If this doesn't work, we're going to try a different way. Is this? So here we're going to do this. Okay, if you do E1 compare, compare to E2. This is going to give you natural order. So, and you're going to change this to negative. It's reverse. All right, see that? You see, this is reverse order. Hey, what do we do this? The traversing is we are internally using the order in order to traverse everything. All right, so next time I'm going to look into the actual code. How do you implement it? You have to provide your own way. How do you implement this iterator? So this is the method that we have to implement. This method we're using here, tree.iterator. So this method has to be implemented. So we will do it. Next time in the class, I'm going to show you how to do this. All right. So this is the example. We design our own data structure and we implement it. And we're going to fit it into the existing Java API. Okay, any questions? All right, if you don't have any questions, have a good weekend. Goodbye.
Thank you.
Thank you. Bye.